Okay. And the next class of active transducers are photoelectric transducers. Let us see this in details. Transducers based on the effect of physical radiation on matter are extensively used in instrumentation. काफ़ी फोटो इलेक्ट्रिक ट्रांसड्यूसर्स यूज़ होते हैं, एप्लीकेशंस होते हैं, ठीक है, डे टू डे लाइफ में, ठीक है. ऑप्टो इलेक्ट्रिक डिवाइस आर डिजाइन फॉर द एमिशन एंड एब्जॉर्प्शन ऑफ द ऑप्टिकल रेडिएशंस. Okay, some of the common terminology which are being used here are, okay, some of the units which are being used. इसको भी again we can classify the two bases. One is radiometric units and another is photometric units. Let us first of all we see that what are radiometric units. Okay, so first unit is radiant energy, which is given as by QE, and it is expressed as joule or hertz. Next, radiant flux, which is nothing but radiant energy per unit time, which is joules per second, expressed as joules per second or watt. And next radiometric unit is radiant ammeters, that is the power per unit area. Okay, one is radiant ammeters and another one is irradiance. Again, this is also power per unit area, but the difference is that one is in the case of ammeters, it is the radiant energy emitted, and in the case of irradiance, it is radiant energy absorbed. Both are expressed in watt per meter square. Okay, now the radiant emitter deals with source of the radiation, and the irradiance refers to the incident radiation. Okay. Now the second class of parameter classifications are I'm sorry, I have to continue with this. Radiant intensity J is equal to dP by d omega. This is power per unit solid angle that is given by radiant intensity, which is watt per steradian. Now the next parameter is radiance, that is dJ by dA cos theta, which is expressed as watt per steradian per meter square, where omega is a solid angle through which the flux from a point source is radiant, where theta is the angle between the line of sight and normal to the surface area dA under consideration. Now, light intensity referring to the amount of power emitted from the source may be expressed in watt per steradian, but generally expressed in photometric unit as lumen per steradian, lumen being the luminous flux. So these were the radiometric units, and there is one more important unit, that is parameter or unit, that is luminous efficacy, which is given by capital A, is used to refer to the amount of luminous flux available per unit radiant flux under, and is given by, that means how much luminous flux is available for a radiant flux. If you are defining one flux in the term of radiant flux, and from that if I want to know that how much from this radiant flux the luminous flux is available, then which is expressed as K is equal to F by W, that is known as luminous efficacy. Another one term comes, that is luminous efficiency, which is K upon K max. Okay, the luminous efficacy upon the maximum luminous efficacy. Now luminous energy for visible radiation is given by integration from 380 nanometer to 760 nanometer K lambda QE lambda D lambda, where lambda is the wavelength of the radiation and K lambda represent the luminous efficacy and the wavelength under consideration. This is the another way of finding a luminous energy. Now we have come to the second set of units, that are photometric units. The first term, it comes to be illuminance. Illuminance is nothing but E is equal to dF by dA, which is lumen, which is given in lumen per meter square, which is nothing but flux per unit area. Luminous emittance again is L is equal to dF by dA again. This is again in lumen per meter square, where L refers for source and E refers for incident light. Now, luminous intensity, which is given by dF, that is luminous emittance or illuminance, luminous flux per unit solid angle, which is dF by d omega, and it is given by lumen per steradian. I is known as candle power, which is a standard SI unit. Luminous intensity, it is a standard unit of luminous intensity, and it is given as candle power and expressed as candela, CD, which is given by abbreviation CD. Now let us move to the last photometric unit, that is luminance, which is given by B, which is again dL by dA cos theta. Okay, this is luminance. Now let us, these were some of the photometric units. Now let us see the photoelectric devices. A photoelectric device is an apparatus that allows the flow of current only when light falls on the device. Okay, photoelectric device is nothing but it is such an arrangement that when the light comes to the device, then the current flows through that device. Also, the magnitude of the current varies with the intensity of the light. It has been found that intensity, as we are increasing the intensity of the light, the magnitude current is also increasing, or decreasing the intensity of light, it is decreasing. Okay, different photoelectric devices which are classified as photoemissive cells, photoconductive cells, photovoltaic cells. Before going into the details, let us first of all understand what is the photoelectric phenomenon. If a light quantum of wavelength lambda interacts with an electron bound in a metal surface, the entire quantum energy is converted into kinetic energy of electron. As soon as a light falls on a material or certain wavelength lambda, it simply interacts with the electron bound to that surface or metal surface or material surface. The entire whatever the energy is being in the light quantum in the form of quantum energy is converted totally into the kinetic energy of the electron. The net energy with which the electron will be able to leave the metal surface is reduced because an amount of energy equal to the E phi is utilized to overcome the binding force of the metal. Okay, now first of all, the kinetic energy is not almost equal to that of energy in the light quantum. Some of the energy is being used by the material, because each and every material have a work function, which is a minimum energy required to get the electron emit from the surface. Okay, so that much amount of energy is being reduced, and rest of the energy is being used as a kinetic energy. Okay, if E phi is equal to SC lambda, if electron in the the product of the electronic charge and the work function is equal to SC, that is SC by lambda, then the net energy of electron becomes zero. If simply the quantum of the light, the quantum energy of the light is almost equal to the energy used by electron for work function, in that case there will be no emission from the metal. It only simply comes out of the metal, but it doesn't travels. Hence, for each material there is a minimum wavelength which is given as lambda naught, known as threshold wavelength, which is normally given by 1240 divided by the phi. That phi is nothing but your work function. And for lambda greater than this value, no electron will release from the surface. This is known as minimum wavelength or threshold wavelength or cutoff wavelength of any material. Below this wavelength, there will be no emission of electron from the metallic surface. Okay, this is the cutoff wavelength, and this is entire phenomena is the basic fundamental phenomena of photoelectric effect. Okay. Now let us see the first class of photoelectric transducer, that is photoemissive cell. There are basically two types of photoemissive cell. One is vacuum type and another is gas type. Vacuum type photocells, it consists of a curved sheet of thin metal with its concave surface coated with a photoemissive material. We simply use a concave sheet of metal which is covered by a photoemissive material, which forms a cathode. It is a cathode and a rod anode mounted in the center of the curvature of the cathode. In the center of the curvature there is a anode. Okay, the whole assembly is mounted in a vacuated glass envelope. There is an vacuated glass envelope as shown in figure. This figure can be seen. Okay, and now the cathode emits electron when light radiates strikes them. As soon as the light wave is striking that particular metal concave cathode, then there is an emission of electron. That emitted electrons are collected by the anode, forming an electric current. Okay, now simple circuit of photocell is shown in figure. This circuit may be used for measuring luminous flux or luminous intensity. It is used for luminous flux or luminous intensity. Now, this is a basic circuit of measuring luminous flux or luminous intensity. As soon as you are increasing the intensity, आप जैसे जैसे इंटेंसिटी बढ़ाते जा रहे हैं वैसे वैसे करंट की वैल्यू होती जा रही है. ठीक है. Why this variation? Why the increment of intensity and the variation of current due to that? You can find out how the intensity of the light is being varied, and you can calculate the luminous flux and luminous intensity. The current through the tube depends upon the following three parameters. First is the intensity of the light. Second is the color of the light or the wavelength of the light. And finally the voltage applied between cathode and anode. These are the three fundamental parameters on which the current through the wire. As soon as you are increasing the intensity of the light, the current is increasing. If you are increasing the wavelength of the light, then also there is the current is affected. And if you are increasing the voltage, which is between cathode and anode, but natural that if you are increasing the voltage, you are attracting the emitted electron more faster. Therefore, again you are increasing the current. Now, figure below show the current versus voltage characteristic of a typical evaporative photocell. This can be the curve. This is a curve between the anode current and the anode voltage. Okay, for different values, you can see that for 0.2 lumen intensity, you are getting the below curve 0.4 lumen intensity, you are getting the second curve 0.6 lumen, you are getting the third curve 0.8 lumen, you are getting the fourth curve, and for the 1 lumen, you are getting the final curve. According to the intensity, there is a variation in the current. This is the variation is shown between the current and the applied voltage. Now, a study of this curve shows that for a constant impressed voltage, the current is proportional to the luminous flux or intensity provided light of the same wavelength is used. Okay. Now, let us see some more parameters of photoemissive cell, which is for the first parameter comes a photoelectric sensitivity, which is defined as S, that is I/B upon phi, where luminous plus phi is expressed in watts. The photoelectric sensitivity is called radiance sensitivity and it is expressed as ampere per watt. Okay, it is expressed as ampere per watt. This is a current per unit luminous flux. Now, photoelectric sensitivity is expressed by in the photoelectric unit is ampere per lumen. The sensitivity of a photocell is moderate. Normally luminous sensitivity is 10 to 100 microampere per lumen, and radiant sensitivity is near about 0.002 to 0.1 microampere per microwatt. Now let us see the advantages of photoemissive cells. They are stable and do not change their characteristics over long period of time. That means they have high stability. You can use them for a prolonged period and without being changed in their characteristics, or you can say that their repeatability and reproducibility is very good. Operate at low voltage. It doesn't require any high voltage supplies. You can operate them with the help of batteries and cells. Okay, now protect against excessive light, and excessive light semi-protected rather, and they are highly protected. And what are disadvantage? Low current lead to low sensitivity. Current key values, you can see that the current values are in the microampere range. Therefore, you can see that there is a low sensitivity due to the low current. Sensitivity of the photocell can be improved by using. You can improve this sensitivity or the current conductivity by applying the gas filled tubes. You can fill the, which is evacuated, you can fill them with the gases, and due to that the conductivity from the cathode to the anode can be increased. And or you can use the photomultipliers, which will be studying in the last topic of the phototransducers. Photomultiplier simply multiplies the photons by using number of anodes and cathodes by increasing the number, and you are simply multiplying that. You can also use that for better sensitivity. Now the gas filled photocells, the sensitivity of the photocells can be increased by amplifying the number of electrons produced by the cathode by a gas discharge. If you are introducing the gas between the cathode and anode in the previous case, which was in the previous case we have used the evacuated glass, but now we are considering a gas in that. Now by the electric discharge of the gas, we can improve the sensitivity and we can amplify the number of electrons being produced. Now only the inert gas are used at a pressure of 1 mm of Hg introduced into the envelope. The emitted electrons are accelerated by the electric field and cause ionization, and thus further electrons are produced by collision. Okay, in the discharge of gas, simply due to the applied electric field, the electrons get striking on the gas and gas electrons, and they are further producing, and they are further increased by the collisions and ionization. Okay, now this process may provide a gain over the response of vacuum cell of about 5 to 10 times. So 5 to 10 times gain can be seen by applying the gas and our photocells. Voltage current characteristics of gas filled photocells are shown in figure. You can see in the case of gas filled photocell, the current behavior with respect to the anode voltage changes little bit, and you can see that the curves are rising, being in the first case that gets saturated, but in this case it is getting rise as soon as you are increasing the voltage. Now if in this case, if your applied voltage exceeds a critical value, depending on the tube geometry and the gas filling and the illumination, a glow discharge may set it, which can damage the cathode. Okay, here the disadvantage or limitation is that because each and every gas has a certain critical voltage, if you are increasing beyond that, you are getting a glow discharge, and which can damage the entire photocell. Therefore, you have to put your voltage below that critical value. Though the luminous sensitivity, which is for this gas type photocells, are 40 to 150 microampere per lumen, and the radiant sensitivity is 0.01 to 0.15 microampere per microwatt. Okay, now let us move to the next transducer, that is photomultiplier, which we were talking before. The photomultiplier is in fact a vacuum photocell with a large number of anodes. There are number of anodes and one cathode. multiple anodes which we use in this photomultiplier are known as dinodes. Okay, electron emit from the cathode due to the illumination is first attracted by the first dynode, and due to electron moving with the high velocity striking the dynode produce a secondary emission. When the high moving electron strikes the dynode due to the high velocity, they simply produce a secondary emission, which the second dynode which is after that, which is after this dynode which is at higher potential attract that secondary emissions, and so on. And due to this, for example, if first dynode attract one electron, and that due to the kinetic energy of that electron which strikes the dynode produces secondary emission, for example 2 or 3 electrons. Okay, then this are again attracted by the next dynode, which again multiply this 3 by again next 3, and you are simply multiplying the number of electrons, and as you are increasing the number of dinodes, your multiplication factor just goes on increase. So each dynode is at higher potential than the previous one, which increases the secondary emission at each step, or electron multiplication take place at each step. Normally you can go up to the amplification of 10 to the power 5 to 10 to the power 9. You can increase the emission tremendously. Now for this case, for the photomultiplier, the sensitivity is of 1 ampere per lumen to 2000 ampere per lumen. Now you have come in the range of ampere. Now till now, for the previous cases for gas and all that, we were in the microampere range, but in this case, if we are using number of diodes, the range comes to in the ampere range, and that is which we can see that it's a good significance value, 1 ampere per lumen or 2000 ampere per lumen. That's a good value. This is how this is the working or construction of a diode. You can see that diode D1 is at some potential, and that D2 is at another potential. In the above figure there we have used a different battery, or you can use the potential divider circuit as shown in the below circuit. So by seeing that, this is how we can improve the photo conductivity by increasing the number of diodes. Now let us see some example. Show that the photoelectric emission to be positive over the whole visible region of 4000 angstrom to 8000 angstrom. The work function of photoemissive surface should be less than 1.5 electron volt. For more simple, it's very simple that he's asking. The question is asking that for this particular range, the minimum work function required is 1.5 electron. You have to prove that. So simply the it's a maximum work function. Photoelectric emission to take place between 4000 to 8000 or 0.4 micrometer to 0. The maximum function is simply you take the formula of 1.24 into 10 to the power minus 6 upon lambda naught. You will take the maximum wavelength, that is 0.8 micrometer. The maximum value of one function will be 1.24 into 10 to the power minus 6 upon 0.8 into 10 to the power minus 6, which comes out to be 1.5 electron volt. Okay, so this is proved. Now let us see the second example. Determine the maximum velocity of the emitted photoelectron when the molybdenum surface having a work function of 4.3 electron volt is irradiated with the mercury light having a wavelength of 2537 angstrom. The E by M ratio is 0.16 into 10 to the power 12 coulomb per kilogram. Now using the mercury light wavelength, we can calculate the energy by the basic formula of 1.24 into 10 to the power minus 6 upon lambda. By putting the value of lambda over here, which is 2537 into 10 to the power minus 7, minus 10, that is, gives out to be 4.89 electron volt. Now this is you can say the work function. Sorry, this is the energy being given to the surface, molybdenum surface. Now as it is given in the question that the molybdenum surface have a work function of 4.3 electron volt. Now you have to simply subtract this value from the energy of the mercury light wavelength, the mercury light energy, so that you can get the value of that kinetic energy of electron which is being emitted from the surface. The maximum energy of the emitted electron will simply 4.8 and minus 4.3, that gives you 0.59, and using this energy you can give the kinetic energy to the electron, which will move with the speed of half mv square, with the speed of v, and which is having a kinetic energy of half mv square. This is equal, this will give you the velocity of under root 2e into energy, that is photo energy upon m, and E by m ratio is already given in the question. You can use that, and 2 into 0.176 into 10 power 12 into 0.59, which gives out to be 0.456 into 10 power 6 meter per second. Now let us move to the next question. Next question says that find the sensitivity of a photomultiplier which has a 6 stage and the gain per stage is 5. Okay, there is a 6 stage and each and every stage is having a gain of 5. The cathode sensitivity is 24 microampere per lumen. If the maximum safe current is 3 ampere, calculate the maximum safe illumination. If its maximum current that it can handle is 3 ampere, we have to find the maximum safe illumination. Now, if the gain of the amplifier tube is g power n, that means total gain of the multiplier will be simply the number of stages, the gain per stage to the power of number of stages, that is 5 to the power 6, that is 15625. Overall sensitivity, now if it is a gain, the overall sensitivity will be simply multiplied by this gain. Okay, that is given as 24 microampere per lumen. That if you multiply this by 15625, you will be getting 0.375 ampere per lumen. Okay, this is the maximum overall sensitivity of the material. Now from this we can calculate the maximum allowable illumination, which is by using the safe current, that is 3 by this sensitivity. You will finally getting the maximum safe illumination in lumens, that will be 8 lumen. This is the maximum value for illumination for which the safe current 3 ampere can be implemented to this photomultiplier. With this, we have completed 2 photoelectric transducers, and the next lecture we will be seeing another 2 or 3 more phototransducers. Till then, have a nice day.